Good morning. Namaste. Shubhodayam. I'm so excited to be here in India for the first time. I've worked with many colleagues in India for over 15 years, and I'm super excited to be here learning about the culture, meeting friends for the first time. I've been all around the world working on security for Microsoft, and so even though India is new and exciting to visit, it also feels friendly and familiar with so many faces. So I want to say, first of all, thanks to everyone for such a warm welcome. I think my slides are going to come up here. All right. So today I'm going to talk to you about two of my favorite things. The first is AI. Anyone heard of it? AI? Heard of it? Some people may call it A1, but AI? Never heard of it before, right? And the second thing is Windows. And so I know all of you who are interested in security are probably pique your interest when you say, how are AI and Windows coming together to be secure? And my goal today is to let you know on the front lines, doing new things, what we've learned in Windows, and how we've learned things can help both offensive and defensive practitioners. So I'm excited to talk to you about this. This is, as Tom said, this is fresh off the presses. So the first thing many of you have noticed is we're in an era where not only is AI pervasive in every application, but it's migrated from just a cloud or web-based service or a small app talking to the cloud to actually move AI on devices. So if you've used a Samsung or equivalent Android phone, I'm sure you've seen many of the possibilities around circle to search, or even in some case, agentic support, which is new in Android, that's happening with tiny models on the device. It's also challenging from a security perspective because essentially LLMs are untrusted data that are now driving applications across the device. And famously, Apple has announced and started to integrate Apple Intelligence, which as it progresses will also challenge how the device itself hosts AI securely and how that operates on the edge. And then finally, in Windows, we've done numerous integrations with AI, from very basic things like the generative AI and things like MS Paint or summarization in Notepad, to much more ambitious and security interesting things like Windows Recall, which I'll talk to you about in just a second as lessons learned. So the first question you might have is, why would you want AI on the device as opposed to it being integrated in the cloud? And there's really three key answers to that. First is we have the compute power on the device, which helps with things like efficiency, environmental aspects, and sustainability, and numerous other computational savings. Cloud is expensive and a finite resource, so more that can be distributed, the more efficient we can get. The second thing is fairly obvious probably to this room, which is privacy. There are many cases where you simply don't want to send information to the cloud. That could be because the cloud is not a compliant environment and you don't feel comfortable with that. That could be because certain models, social media models, et cetera, may actually use that to profile you for ads. Or you could simply feel emotionally uncomfortable with doing things like making friends with your AI or having social interactions, and that going into a place where you don't control the data. So we've seen an increasing demand for users to move AI into a place where they control the data. And then finally, more practical things like network latency. For example, I experienced this as I'm traversing numerous countries. There are different qualities of service. And when AI becomes critical path, like it has for me and many others in this room, just simple access to it becomes important. So those are three key reasons why we've introduced both hardware support in the form of new PCs that we call Copilot Plus PCs for AI across Windows, but it's also something that we've started to integrate into the software. So let me tell you about what that means from a security perspective. But first, I just want to give a basic sort of overview of how we leverage hardware to produce this. So at its most fundamental form, most generative models operate on a simple construct or primitive called a tensor, right? And that fundamental tensor may exist in very common neural network software like PyTorch or TensorFlow. Traditional GPUs are excellent at taking lots of power and providing lots of computation. But they're also arguably more complex than they need to be to do simply neural networks. For example, a NVIDIA GPU, like an Ampere series GPU, is Turing complete. It has conditional branching, It has speculative execution. In many ways, it looks very similar to a CPU, which gives it great flexibility, but also increases its cost and its power consumption. So when we were thinking about, in Windows and Surface and devices across the ecosystem, how we would provide compute power, like 50 terabytes of compute power, but not impact battery, we moved into using things like the NPU, or neural processing unit, which is a simple ASIC, which doesn't have as much computation complexity, and therefore can compute on tensors, do these matrix operations at a much more efficient, in a much more efficient way. And so these neural processing units, or tensor processing units, these specialized ASICs, have become commonplace across almost every Android, ARM, or even x86 chipset. Now, the next thing I want folks to understand is AI itself has been integrated deeply in the Windows operating system, and there's an important reason why. We want to be able to abstract, to bring as many existing models into Windows without AI engineers having to rewrite their software. We truly would like to support write once, run anywhere. So whether your backend is CUDA, an AMD backend like ROCm, or you want to use an Onyx model, which will write once, run anywhere, we want to support that on the NPU. So Windows has used first-class runtimes to take things, whether it be a web app or a native app, convert it into an intermediary language that can then be supported on NPUs. And this has made it possible to bring many different generative AI or neural network models on device to leverage the NPU and get that power and efficiency, which really opens up a new world of applications, but also a new world of attack surface. So let's talk a little bit about what the on-device AI threat model is today. And I'm going to even talk to you by the end of my talk why it may be changing in just a few short weeks and months. This is exciting and maybe scary because the pace of evolution is breakneck. As fast as AI threats are moving, so are the security considerations. But there are really three primary categories for on-device, specifically AI. The first is data attacks. This was actually a bit of a surprise to me. When I was starting to think about how we would do AI securely on device, I speculated the biggest security challenge would be around model tampering or traditional attacks like cross-prompt injection. What we found pretty soon was one of the bigger threats, arguably the largest threat, is not so much the AI itself, but the security of the data that is necessary to either do inference or train a model. In other words, in the AI world, in an agentic operating system, you're encouraged to store data because you now have the computational power to process it for insights. And so that could be large data caches like screenshots, text, imagery, video, very sensitive data, both for inference and training. And this becomes a potential exfiltration target. So even though AI itself is not being attacked, the fact that there's so much data now on mobile devices and laptops is an increasing concern. The second thing is model attacks, like model tampering or even IP threats of model weight extraction for closed frontier-level models. This is particularly interesting because we're seeing more cases where the model itself will be in the critical path of the security decision. The simplest one I can think of, which I'll talk about in detail in just a second, is something like Windows Hello. Windows Hello makes authentication or authorization decisions. So being able to tamper with that face or fingerprint biometric model, which is essentially a neural network, could end up in a direct security attack. But also, we have companies who have spent hundreds of millions, if not billions of dollars training their models, and protecting their intellectual property in the form of model weights becomes important. And then finally, for on-device training, and in some cases inference, poisoning the model instead of directly tampering with it becomes interesting. And then finally, I think this is the area maybe of the most expanding research, which is there are processing power and capabilities that now exist on device, which could be game changers for post-compromise tradecraft. I'll talk about an example in just a minute, but the ability to search and rapidly extract from information, for example, using an object extraction, text recognition, that means the speed of exfiltration and the precision of post-compromise tradecraft increases immensely. A world in which interpreter or any other C2 framework is integrated into AI for fast searching is a world in which attackers become more efficient, in some cases, than defenders. And that's something we want to look for. I thought this was an ominous but accurate quote from a security researcher at Kaspersky after they suffered an attack on iOS phones, a full-chain zero-day exploit that used AI in the C2. In the future, malware will just have to ask AI what it knows about you. We should prepare for that. I think that day has come, and I'll tell you why. A great example of this in the real world, and again, I'm not here to market to you, I'm here to share real-world information, happened over 2 years ago. And that's something that was called Operation Triangulation. This was an attack on Kaspersky, the security company in Russia, and it leveraged a full-chain iOS exploit to compromise the devices of Kaspersky employees to do counter-surveillance, IP, et cetera. More interestingly, this full-chain exploit did something for the first time we've seen in public. It leveraged AI APIs, OpenCL-based APIs that are on iOS, to dig through large data caches on phones, right? Modern phones have 512 gigs, 1 terabyte. I have a 2 terabyte iPhone because I want to keep everything on my phone. And just the task of compromising a phone, finding what you want, and then exfiltrating it over a cellular network is an incredible challenge for attackers. You can't just download 512 terabytes off a phone after you compromise it. You've got to find things. And what we found in Operation Triangulation is the attackers leveraged the AI APIs on iOS to figure out what they were looking for. In this case, they were looking for documents and text. So they were able to query against the photo apps once they had full access to the device, full privileges, to say, show me which documents are in the photo spool. Show me this text if it exists in the photo spool. Show me this person's face in the photo cache. That is an incredibly precise and game-changing capability for attackers. If you think about this, without AI, they might have had to exfil hundreds of gigabytes of data. Maybe they ended up with a bunch of cat memes instead of what they wanted. But with this capability, as an attacker, you can very quickly target what you want. And I think this will become a very interesting post-compromise vector. Now, I want to give you another example of real-world model tampering and what that might look like. I mentioned previously that Windows Hello is a good example of AI in the critical path of decision-making. Passkeys, multi-factor authentication are all leveraging Windows Hello to make decisions. If that can no longer be trusted or it's undermined, the security of the entire device is undermined, and this is a real-world AI attack. So Windows Hello attack surface traditionally is actually in what we call the normal world operating system, which means it's susceptible to tampering from administrative attacks. Administrators can modify the binary on disk, they can do code injection, they can modify the fingerprint or face matching data models. There are numerous sort of attacks for them. And if we walk through this with things like virtualization-based security, we can actually take a lot of those models and move them across the security boundary. So a hypervisor in the context of areas like Azure actually provide multi-tenancy. What that means is an admin-level attacker in one tenant cannot cross over. And so by taking the models and moving them out of normal world and into this secure virtual environment, we're protecting the model from tampering, which is an incredibly important approach. So what that might look like in the normal world is, if I can just go back, is you might have the ability to do leaking or injection against the sensor itself. You might be able to sniff information as it traverses normal world, especially if you're an administrative level attacker. You could modify the matching code, et cetera. But in the virtualization-based world, we create this boundary, and we also take the sensors. In Windows, this is called enhanced single sign-on. We take the sensors and we route them directly to the secure virtual machine or trusted execution environment. This means traversal attacks over over normal world are no longer possible to be sniffed or tampered with, even from administrative level attackers. So this is a great example of taking an existing sort of attack surface, moving it across a trusted boundary by making architectural changes, and then making hardware modifications to really complete the scenario. And I'll touch on in just a moment why it's so important for Windows Hello and other similar AI models to become more secure because we're going to leverage them more often. So runtime authorization has become a much more critical capability on Windows. There are two things we're doing at the architectural level that are very important. The first is we're moving from a world in where Windows users are running as admins all the time to what we call an adminless world, where users are running as standard users and authorize specific operations that require privileges. This is, in comparative terms, pretty similar to sudo on Linux or on Mac using their authorization framework. So when you want to do something like load a driver or change a firewall rule, this year in Windows, you will be required to use Windows Hello, Face, or Fingerprint. This is one of the reasons that we want to make sure that the neural networks that power this biometric matching are secure. And this is similar to what you would do with Face ID or Touch ID on a phone, right? In a regular course of doing things, whether you're autofilling a credit card, releasing cookies, et cetera, it's much more common to do runtime authorization. And this will become more important in a second. So with the Windows Hello sign-on security architecture, we're able to make runtime authorization significantly more secure. And this is going to help us when we get into the data attack space. So data threats from AI are, again, just to reiterate, these large-level data caches that exist for inference. There are two real strategies for securing this data. The first is the strategy taken by iOS. Things like Spotlight or the AI object extraction and matching capabilities, which we just talked about, are secured not by armoring the data cache, but by instead putting in front of attackers multiple rings of protection. So for example, on an iOS device, you've got to first find an exploit. You've got to bypass exploit mitigations. You have to get a kernel exploit, which will allow you to disable iOS integrity frameworks. You have to disable, for example, file system persistence. And once you get all that, then the data is accessible to you. It's not protected at runtime. On Windows, we have an open platform that's much more extensible. So we don't have code signing all of the time. We don't have as much privilege restriction in terms of mandatory sandboxing. So our approach needs to be more rearward in protecting AI-based data caches. We have to find a place that's secure from the admin. We've taken this ladder so that we can maintain parity in security with iOS while having a more open platform. And I want to talk to you about the feature that leverages this. So Windows Recall is a very interesting feature that takes screenshots and saves context into a database as you use your machine. The idea is that you can have perfect recall of anything using simple semantic searching, which is very interesting. So for example, I could say, show me the Teams meeting where Tom was wearing the blue shirt, or where someone was wearing a T-shirt that said BlueHat. And I can type this into Windows Recall. It will take me to the exact image that has this. That image will be processed and have object extraction. So you could get even more abstract. You could say, where someone sort of looked like a cat, I don't remember, maybe some other type of small mammal. You can get very, very loose in your searches. And not only will you get a perfect screenshot of that through this sort of semantic capability, you'll also get context, which means you can click on that image and have it open Teams exactly to that meeting. So you can see this is incredibly powerful for being able to multitask and move along and collect data without having to sort of reason or have another data cache. The challenge with this is also an incredibly sensitive data cache that we need to protect. So obviously, having a set of screenshots is something we need to make sure we secure, but it's not just that. One of the things we do in Windows Recall is we give you a lot of optionality over where we store screenshots. This is for privacy reasons. So you might want to say things like, I only store things for a day because that's what I'm comfortable with. Or I only store things for sensitive apps. In the case of an admin level attacker, they might seek to use Recall as a data collection or monitoring system. And so we've got to make sure that this configuration of security options is also protected. And then finally, there's a concept of write-along. So even if we allow access to this data through runtime authorization, attackers might use that window of when this data access has been allowed to sort of write along and access it. So these are all intrinsic threats to something like Windows Recall. And let's talk about some of the techniques we use to solve it. So our approach for Windows Recall was to encrypt all important data elements. So all of the data cache, all of the databases related to that, search terms, they're all encrypted at rest and at runtime through segmentation into this separate trusted execution environment, which we call virtualization-based security. In addition, it's not sufficient to just encrypt things. We need to make sure the keys themselves, the private keys, are stored securely. So we not only store securely the keys themselves, but we also isolate the encryption algorithms and runtimes that do encryption decryption. Additionally, we want to make sure that the user themselves, who configured recall and decided to set it up on the machine, is the user who has login privileges. This would prevent someone from snooping on your password, coming to your device when you're not there, and then turning on recall as a surveillance mechanism. That's a real concern that we want to address. So having proof of presence with things like biometrics, where we can rely on this enhanced biometric path that we talked about with Windows Hello, is key to this strategy here. Finally, we have a very difficult problem to solve in the context of Windows Recall. We want to protect the data from the user who has the right to access it. I'll say that again. We want to protect the data from the user that has the rights to access it. What do we mean by that? Well, in a confused deputy attack, like when malware takes over your machine, an API or endpoint doesn't know whether the user is actually attempting to authorize something or if it's malware running in the context of the user requesting to access that. So we have a couple of ways in which we protect against this. The first is we make sure that there is biometric runtime authorization, and then there's a timeout window for that. This is pretty similar to what you might see in like a password manager or the like. In addition, we want to make sure that a malware attacker can't simply continue to query and hammer the API from the normal world into the trusted execution environment. So think something like Cloudflare. So we implement an anti-hammering against the API endpoints to make sure someone can't say, I want all cats, I want all dogs, I want all documents over and over again until they've slurped the entire database. So these are very interesting problems that hadn't had to be solved before AI pushed us in the direction to have more data on the device. So the end architecture is something like this. All snapshots are processed in a virtualization-based enclave or trusted execution environment. Right after a screenshot is taken, it's encrypted with the public key of the user, and the private key is stored in the TPM and only released during biometric matching. And all cryptographic operations, encryption and decryption, happen across this boundary. The second thing is, in order to authorize data for a short period of time, a user needs to do a biometric authorization, and I talked to you about why that's secure from administrative level attackers. We require proof of presence to set up for the first place to mitigate any potential monitoring or surveillance concerns. And then finally, we have anti-tampering and tamper-proof settings to make sure people that get to administrative levels can't undermine this. And while we developed this in the context of recall, this entire design pattern is reusable for future first and third-party AI on device that will have similar security concerns. So given that, let's talk about the future, because the future is bold and very interesting. The first thing is we have challenges in defense, and we need to modify our architecture to move towards what we're calling an agentic OS, where agents are first-class citizens and highly secure. And that means we need to make sure that the MPU and GPUs are available directly from trusted execution environments where they're not there. We also need to consider whether Microsoft should have the ability from an insider attack or through even legally compelled orders to have access to this data. In Azure, we have something called confidential compute, where Microsoft is entirely out of the trusted computing base and outside of the trust model altogether. And we aspire to get to the same thing on the device. So if you think about our architecture today for both Hello and Recall, things would get significantly better if we could offer hardware-based confidentiality for the VMs segmenting this data. So confidential VMs are completely isolated from the hypervisor and host OS, and they run in what's called a paravisor, which is supported directly by the silicon vendor. Every CVM is encrypted in memory during use, and those encryption keys are stored in hardware registers and inaccessible even directly to the Microsoft-produced hypervisor. The underlying OS disks, which in many cases could be a virtual hard disk, are encrypted at rest, and the ability to manage these operating systems disks today are predicated on what we call BYOK, or bring your own key to an HSM. This is how it works in Azure today. What we'd like to do is combine the usage on device of confidential computing for cloud and move it onto device. And there's a few ways we can do that. Primarily, we need hardware support in the next generation of client CPUs for these paravisors, and as well as the CVM firmware that is authored directly by the CPU vendor. We want to make sure that the hardware-based Ts have access to TPMs, NPUs, and GPUs, and that all of the guest operating systems are measured and can be attested separately. The reason this is important is we'd like third-party vendors to be able to say, I only run my AI system that's highly sensitive in this confidential-based system that even Microsoft can't undermine, and that requires the ability to do measurements essentially from the earliest forms of boot and do that independently in a high-integrity cryptographic protocol. The confidential computing threat model today is very strong with the exception of one area. And I salute AMD as being one of the only CPU vendors that is very transparent in their attack surfaces. But if you look very closely, you'll see there's really one area in which the latest generation of confidential compute is not highly secure, and that's against physical access. So again, confidential VMs are great at protecting against software attacks. They are out of scope or do not offer protection against hardware-based attacks. So are we going to get confidential VM hardware on consumer CPUs? Today, we do not have that, and we're only able to approximate. The closest we can do is use the 10,000 lines of hypervisor code to isolate keys. That, in a nutshell, means we cannot distrust Microsoft. Microsoft is still in the trust boundary, but we're working diligently with CPU vendors to bring this Azure-level hardware-based confidential compute onto software. But today, the best we can do is what we call virtualization-based CVM, where the keys themselves are held in a small, trusted computing base of the hypervisor and not in hardware registers. The last missing component into completing a perfectly confidential AI system on device is confidential GPU. Today, a good example of that is NVIDIA's Ampere protected memory system that exists on A100 and H100 Tensor GPUs. That uses a combination of shared keys and mutual authentication to create a secure channel between encrypted memory and multi-tenant support on a GPU and CPU. This means you can have end-to-end encryption for both at rest and at runtime, even across AI model weights, which is super important for tampering attacks, et cetera. If you're curious, so just for a second, here's what that architecture looks like in Azure. And there's significant challenges to bring that to client, but it's something we're working through. We're not the only ones pioneering in this space. Apple is known for being a very privacy-centric company. And one of the things that they're claiming is instead of doing as much model and data processing on the client, they're doing it in the cloud with equivalent privacy because they've designed a proprietary system for confidential compute, which looks very interesting. They've published a white paper on this, and I salute Apple for using some of these new technological constructs, these primitives, to push privacy and AI forward. The last thing I want to touch on is something brand new that we're thinking about. Many of you probably seen blog posts, LinkedIn posts, et cetera, on MCP or Model Context Protocol. In short, this is a discovery and IPC mechanism for exposing tools to LLMs. So you can expose calculators by wrapping an MCP server interface around calculator. You could do this for any arbitrary Win32 application. Most of the communication in IPC is done either over standard I/O or even local loopback HTTP, and usually the transport mechanism is JSON RFPC. There are numerous security risks with exposing MCP directly to a Windows operating system. That includes the fact that MCP standards for auth are immature. We're just in the process of defining things like OAuth to make sure that that IPC mechanism is safe. MCP servers on Windows today could run without any limitations, which means cross-prompt injection becomes RCE, which you can imagine how interesting that is. And then from the registries we've seen out on the internet, for example, on GitHub, there's lots of low-quality MCP servers. And finally, untrustworthy servers can snoop on data or even Trojan devices and changing their implementation all the time, and they're very hard to detect. CUAs, or computer-using agents, are very similar. Microsoft recently announced in Copilot Studio for UI that we support computer-using agents, which do screen processing and drive input through mouse and keyboard to mimic human operations on a machine. There's also things like OpenAI's Operator. They have numerous security risks as well. They're taking screenshots, they're processing, they're taking that information back, and then they're driving input, all of which have significant attack surface and need to be very precisely secured. Things like prompt injection, which today could go from passing a simple URL and poisoning things like model memory to generate arbitrary operations. Tomorrow, with things like CUA or MCP, that becomes remote code execution. So Windows CUA has numerous challenges around this. So for example, we would like to do asynchronous processing, which is allow a user to describe via a prompt automated operations to be completed via CUA. We need to account for being able to do this asynchronously. Windows has one UI thread, which means a separate session would need to be spawned for this, and that session would need to be strongly audited, and human-in-the-loop decision-making would need to be present for all secure operations. This is something we are looking at deeply to make Windows the first agentic OS, and there are numerous challenges along the way for that. So those prompt injections could become, again, arbitrary operations that can be done by a computer user agent, which is the executor in this model. As an example, using a benchmark called OS World, OpenAI's operator model, which takes screenshots and does operation, is accurate about 30% of the time. So you can imagine with influence over the prompt and absence of perfect accuracy, CUA will become a very interesting attack surface. So stay tuned. This is something we're looking at deeply in Windows. And finally, I want to leave you with this, the security implications for on-device AI. Ultimately, there are some opportunities for attackers to increase the capabilities of on-device tradecraft using AI capabilities, like those exemplified in the attacks on the iOS phone. Hypervisor bypasses will become significantly more impactful on clients. Today, they're already impactful in the cloud, but they'll be impactful on clients as they become more critical path for things like authentication operations. And we expect to see increasing attacks against the UI and T interaction as AI becomes more of an interesting attack surface for post-compromised tradecraft. In defense, we need to make CVMs and GPUs ubiquitous across all devices. We need to leverage software CVM until those hardware capabilities are available. And we need to provide greater transparency about what's happening in the T through ledgers and attestation. And then finally, you should look for more in the near future about how Windows architecturally is changing to make MCP and CUA usage secure. And with that, I thank you so much for having me today. This doesn't like me, but thank you very much. I appreciate it.